Hi there, welcome. I'm Noel.
I'm Emma.
We're going to talk to you today about machine learning using Earth Engine's built-in classifiers. So I'm going to present a bit about how Earth Engine classifiers work and some tips and tricks on how to use them. And then Emma's going to present on work she's done on ensembles. All right, just to put us all on the same page, I'm going to talk about things that look like Landcover maps. The way that those typically get made in Earth Engine is that you start with some points, either some locations that you've sampled in the field or some random locations, but either way they're labeled. And so maybe they get labeled by sampling from an existing Landcover map, or maybe they are hand-labeled points. And then you have some covariates, something like Landsat data or Sentinel data or some kind of SAR data. At each of the points that you've come with, you sample the covariates, and you end up building a table of one row for each point that has the covariate values at that location and the classification, or the supervised value, and that's what you end up building your classifier with. So that's the basics of how it all works, and we'll talk more about that in a second here. But the actual practice of doing this in Earth Engine looks like this: sampling, training, classification, assessment. And doing that is a pretty simple process. If you show up with training data, you can build a basic classification with these, 9 lines of code here. You can actually do it with less, but this is sort of the recommended practice, where we will sample some region, extract a bunch of training data, sort that data so that we can take some of it and use it as validation data, and we'll put the rest into training. We build a classifier and train with that data. Then we might classify our original covariates, like our Landsat data, just so we've got the map. But then doing some error assessment, where you take the holdout data that you held out earlier, classify it, and see how it compares to the class values that you came with. So that's more or less the whole thing. But there are, of course, all kinds of variations on each of these steps, and that's part of what I'm going to talk about, and the problems that you're likely to run into. In terms of doing classification, we have a bunch of different types of classifiers built into Earth Engine. The ones that most people end up using are cart and random forest. And random forest is really just a bunch of carts put together. Some people really like SVMs, support vector machines. And then there's a minimum distance classifier that people use for a few pieces. The rest tend to be sort of special purpose. If you're doing species distribution modeling, you might really like maxent. People use naive Bayes for various reasons, but it has issues. But you get to pick which type of classifier you want to use. And then the different classifiers support different types of output modes. You might be doing a classification like the Landcover map I just talked about making, where you're splitting things into 2 classes or 3 classes or 10 classes. Or you might be trying to do some kind of regression where you're fitting some curve, like you might be trying to fit a quantitative number like water quality based on some training data. So there's a regression mode, there's a classification mode, and there's a probability mode, which will tell you in some cases how likely it is that the answer is correct, based on things like the votes from a bunch of trees in random forest. And so it's just how many trees, what percentage of the trees voted for the final output number. There's a couple other regression modes, or a couple of other modes built in that allow you more information. So if you are doing multi-class classification, you can actually get a probability for each of the classes. So instead of just doing one class, you can actually do fuzzy classification, where class 1 was voted for 60% of the time, but class 2 was voted for 20% of the time, and you might have some value getting that value out. Additionally, there's a raw mode that's just, here are the votes from all the trees, or whatever other internal representation the classifier has. And there's a raw regression mode that matches that, which is just the different regression values that the multiple trees might produce. Not all the classifiers support all of the output modes. Here's sort of a breakdown of how that works. Random forest is the only one that supports raw regression, for instance. So you might find this list useful as you go and try to get something done. All right, so that's the basics. Now I'm going to talk about things that you're going to run into as you try to scale this up. if you do a small classification, if you've got 10,000 points, you're sampling some Landsat data, you're doing a country scale classification, you're unlikely to hit most of these problems. But as you scale things up, you'll start running into problems. And those problems often look like this. We try to hide how things operate in Earth Engine from you. You typically don't know how many classifiers, how many machines your classifier is running on. You typically don't know which data center it's running in. All those details we hide from you. But as you scale up, you start to find the limits of the system, and those are often multifaceted. So sometimes you'll hit memory limits, sometimes you'll be unable to run something interactively because it's just going to take too long, and sometimes you'll butt up against the limitations of our cache. So inevitably, as you work for bigger and bigger classifications, you're going to try to find some location inside of this triangle that works without actually getting to see the triangle. Right? This is really sort of a black box, and you're just sort of navigating to figure out whether or not you're inside the triangle. So I'm going to give you some pointers on how to stay inside the good part and things you can do to avoid some of the problems that you're going to hit. So one of the main problems you hit is you're trying to do something interactively that just takes too long. If you want to sample 1 million points out of a deep stack of Landsat images, that might not finish in under 5 minutes. And that's the amount of time you get for an interactive computation. So you might need to break it up into pieces. You might need to do an intermediate export. If it doesn't fit in 300 seconds, you got to do something else. So we'll talk about some of the something else's you can do here. You can also run out of memory. There's a canonical sort of 2 gigabyte stack depth that we have, and that's hard to figure out exactly what that means, but it roughly means that you can get about 2,000 values per pixel before you start running out of memory. That turns into something like a stack of 100 images, depending on how big those images are in terms of bit depth, how many bands they've got, that sort of stuff. So navigating that stack depth is tricky. And sometimes you'll hit the most often one you'll hit is the computed object too large. And we realize that this message doesn't mean anything, especially since you can't do anything about them. But all of the training data that you put into a classifier and the classifier itself have to fit into our cache system. And that cache system is limited to 100 megabytes. And so you'll bounce off this limit pretty frequently as you get bigger. So we'll talk about how to deal with each of these in different pieces here. All right, so some techniques to avoid this. The big problem is this 100 megabyte cache limit. You have to fit both the table that you're training with and the final classifier into 100 megabytes. One of the ways that you're most likely to hit that is if you're trying to do a big training data extraction. All right, so here's an actual example with a group I was working with trying to build a forest map using, I think it's 150,000 training points in Europe. And the researcher I was working with did the small red box in the bottom left in Spain and said, it worked in Spain, this will work, like we're going to be able to get there. And then he tried to do the whole of Europe, and it blew up. And well, that's because you extract 150,000 points times 10 bands, times 4 seasons, times a few other things, and suddenly your table of training data is way more than 100,000 points. If you're an Earth Engine user, you might hit this point and go, I know what to do. What I'm going to do is instead of extracting the whole table at once, I will map over each of those points and do an extraction for each one. And so this is the extreme opposite of doing the table at once. This is essentially a separate table for every point. And this will work. You can totally bypass almost all the memory limits in this process. The downside of doing this is that every one of those points goes into the cache on its own. And when we want to pull all that data back in to try to put it into the classifier, we have to read all those values out of the cache. We can read about 100 a second, and so there is a limit of 300 times 100 per second that you're going to be able to read out in the process of doing this to get them into the classifier. So you're going to run out of time. You've traded cache space for time in that triangle, and you can easily fall off the other edge of the triangle just by trying to avoid the cache limits. The cool thing that I discovered as I was helping this researcher do this process is that there's a nice sort of Goldilocks example, or right in the middle. what you can do is you can take your region and you can cut it up into smaller regions. And for each of those regions, you can run a table all at once, mapping over each region, do a reduce regions to all the points in that region, and then put them all together at the end and flatten that out. Among other things, this means that any one table is not too big. They're 1/16th the size, or what have I got here, 20? Yeah, 1/20th the size, give or take. And they actually run in parallel, so it's actually faster to run it this way if you are running out of time. The problem that you might hit here is that if you flatten them all out and then try to stuff them into the classifier, you may still end up with a table that's larger than 100 megabytes. And so there is another step where you can actually not flatten the table, and you can train a classifier multiple times. You can call train over and over and over, and it will just keep stuffing more data into the classifier. So we've got 20 tables. Here we're just mapping the extract function over each of those regions, and then once we've got them all, we map those into training the classifier. Does that make sense? Yeah? Multiple trainings, multiple tables, split it up into pieces. Similarly, you can do this in other ways. You might want to build or train once per land cover class. So if you're extracting 10 land cover classes from some training data set, you can actually call train 10 times, once for each of the land cover classes. Same idea, just split by class instead of by region. Okay, another problem that you'll frequently hit is an out-of-memory limit as the stack depth gets very large. So if you're trying to do 40 years of Landsat for anything, you will sometimes hit this limit just because there are sometimes more than 2,000 images in a location. The secret sauce here for making this work is a parameter called tile scale. When you hit an out-of-memory, most of the time it's on some kind of aggregation like a reduced regions, and most of the time there's an opportunity to specify smaller tiles. And this is moving another direction in that triangle of memory for time. So if you specify a tile scale of 4, it's going to use 4 times smaller tiles, but that means you need 16 times as many tiles in the process. So you are doing 16 times as much plumbing, is what we call it, which can take more time. So you're trading memory for time here, moving on another axis of the triangle. But usually this will fix your problem. A lot of people just say, I don't care, I'm going to set tile scale to the maximum, which is 16. Don't do that. This will make your computation 256 times slower. So you really want this number as low as you can make it, where you don't hit the memory limits, but it runs as fast as it can. Okay. All right, so the punchlines for all those things. If your training table is too large, you hit computed object is too large, break it up into multiple tables. If you hit a training timeout, break it up for more parallelism and separate caching, or just export the whole table. That tends to be sort of the catch-all for a lot of the problems is stop trying to do everything interactively in one session, export a training table, export your covariates. That often will fix a lot of those problems. If your combined training table is too large, you can call train multiple times. If your classifier is too large, now you've got some problems. Your main issues are simply that, or your main solutions here are simply you need to make your classifier smaller by perhaps specifying a smaller number of trees, or specifying for it to stop bifurcating at some limit. And that argument's called min leaf population. In random forest, often it will just keep splitting the forest until you've got one pixel in each bin. And that can end up with a very large tree, which takes a very large amount of memory, which doesn't fit in memory. So min leaf population or fewer trees. And if you hit an out of memory while extracting training data, you want to use a tile scale to make your aggregation use smaller tiles. Okay. I'm not sure I hit that button. Let's try again. There we go. All right. So now I'm going to talk about some other techniques that will perhaps help you get a better result. The first one I'm going to talk about is random sampling. This is a thing people frequently want to do to avoid bias in their sampling data. And there's a couple ways to do it. Some are better than others. One of the easiest ways to do it is the sample function will just let you specify subsampling. So you say, I want 10% of the pixels. It will throw away 9 out of 10 as it samples them. But it had to sample them in the first place. And so this can be very slow because you're touching every single pixel and really just taking approximately every 10th one. It's got issues. Another thing you often do for sampling is sample regions, but sample regions doesn't have any subsampling, so there's no randomness built in. Both sample and sample regions do exhaustive sampling. They extract every single pixel. Sample at least gives you the ability to take a few of them, but sample regions does not. If you've got 3 polygons, it's going to take every pixel and every polygon and give you your output. You might be able to add a random column and filter those down to a smaller number of things, but you still ended up doing the exhaustive sampling in the first place, and that might hit the limits of the system. But some other ways to do random sampling are to make a bunch of random points and then sample at those random points. This is actually what sample does when you give it a smaller number of points. If you say, do 1,000 points, it will generate 1,000 random points by calling the random points function directly and then sample at each one of those points. And this works okay, except that if some of those points, it just throws 1,000 random points into your region or onto the planet, depending on how you specified it. If some of those points fall off of your data, if they fall into masked areas, or that's Cuba, where I've asked for 300 points, and really only about 50 of those points actually land on Cuba. So the rest of them will be sampled, but there's nothing there, so the point is thrown away. So even though I asked for 300 random points here, I'm really only going to get 50 in my sampling result. So both of these methods are problematic because they don't really take into account masking in terms of the numbers that you're going to get. As I mentioned just a second ago, you can also filter down from something like sample regions or sample by adding a random column and then just filtering for that column being less than some number or greater than some number. This would get you 90% of the data. If you reverse the sign to be less than instead of greater than, it would get you 10% of the data. All that said, the right answer is usually stratified random sampling, even if you've only got one class. Everything that we learned about sampling and masking and doing all the right things got folded up into a function built later, which is stratified sample. You can specify, I want 300 points, and it will give you exactly 300 points if they exist. It does a very good job of distributing the points, typically with no biases, and it gives you lots of control. You can actually say, I want 300 points for this class, 500 points for that class, 1,000 points for every other class, and do some fine-grained control on how many points you're going to get out of it. All of these functions, sample regions, and stratified sample, throw away points that are masked, even if only one of the bands is masked. So a common problem is that somewhere in 2021, the thermal instrument on Landsat stopped working, and there's 3 months of data where there's no thermal data. And nobody really knows this. It's not, I mean, it's advertised, it's published, but nobody ever remembers. And so they'll be working in 2019 and everything's fine. They'll be working in 2020 and everything's fine. And they'll sample for 2021 and they're not going to get any data. The sampling produces 0 values. Like, what's going on? You guys screwed up. What's going on? No, what happened is there's no band 10 values. They're masked. Sample looked at it, said, oh, one of these values is masked. You can't train with masked values, and it throws away the whole point. So be careful. If you're getting way less values than you expected, or maybe even 0 values, often it's just the case that one of your bands is masked. And it might not even be a band that you care about. In Sentinel-2, there are 3 quality bands, 2 of which are completely empty. If you happen to sample them because you didn't throw them away before sampling, you're never going to get any points because they're all masked. So keep that in mind. All right, so you do a stratified sampling. It looks something like this. This is, I think, NLCD Landcover sampled with 4 of the classes, 5 of the classes maybe. And you can see a lot of these points jumble up, right? I asked for, I think, 100 points in each class. The only urban area in this region is that one little town, and so the points there are much closer together than the forest points or the water points or whatever. This can lead to problems involving spatial autocorrelation. So I'm going to talk a little bit about how to avoid spatial autocorrelation. And this is a blog post that I made about 2 years ago, but it's cool and it's got really nice pictures, which is really the important part, right? So spatial autocorrelation is when you've got points very near each other. If you sample 100 points from the same field, 99 of those points are probably exactly the same as the first one, and that can cause a problem. One of the ways to avoid spatial autocorrelation is to buffer your points. You say, I only want points that are 1 kilometer apart or 10 kilometers apart. A good way to do that is something like this. This is a random image in a particular projection. So I think this is the North American Albers projection at 10 kilometers per pixel, or maybe 50 kilometers per pixel. Doesn't matter. It's just the buffering that I want on my pixels, say 50 kilometers. So no pixels closer than 50 kilometers together. So I make a random image like this, and then inside each one of these squares, I make another random number. I generate a set of random numbers based on the projection that I actually care about. So maybe I'm extracting Landsat data at 30 meters per pixel. I've got this 50 kilometer big pixel, and inside of that, I've got a gazillion 30 meter pixels, all also random, and I just find the maximum inside of each big pixel. And that will be a random point. These points are, on average, 50 kilometers apart. If I really, really don't want any 2 points to be closer than 50 kilometers to each other, I can actually just cut out every other square, or every other square, cut out 1 out of 8 squares. And then now, no 2 pixels can be closer than 50 kilometers, and on average, they're between 50 and 100. Can you see the little white dots? Yeah, you can see them. OK. So now I mask off everything that's not a white dot, and I've got my locations. I've got a bunch of random locations that I can just extract with reduced to vectors. If you happen to be, so there's an example. If you happen to be the kind of person that really likes doing this with hex, there's an addition to this blog post that will show you how to do this with hex tiles instead of squares. The nice thing about it, it gives you points that are more packed. Yeah. Anyway, it's cool. Okay, onward. Talking about feature vectors, how to make a good classification and some techniques you can use to make a good feature vector for your classification. So here's a bunch of, I think this is Landsat data for 1 year, showing roughly the phenology of perhaps a crop field. One thing that lots of people do to simplify this data down to something you can classify is they'll just take something like a median over that data. And this is a pretty representative number. It's going to be high for places where there's, in this vegetation index, it's going to be high for places where there's vegetation, and it's going to be low for places where it's not. So it might be enough information for the classifier to tell you what's going on, but it's not going to help you distinguish between corn and soybean. You've thrown away all the phenological information. You've just said, my NDVI is pretty high for most of the year by taking something like an annual median. There are other options. You can actually take multiple percentiles. So the median is the 50th percentile, but there are researchers that take multiple percentiles. So 10th, 25th, 50th, 75th, 90th, and differences of those percentiles even. And again, there's a little more information here. This is highly weighted towards the top of the NDVI scale, right? The numbers at the top are closer together. There's more phenological information built into this and more for the classifier to work on, but it's still probably not diagnostic. It's not going to, again, tell you corn versus soybean. For something like that, a thing that you can do, here's how you compute the percentiles. It's quite simple. But a thing you can do instead of doing a number for the whole year is to break the year up into seasons, for instance, or even months, and then do some statistical aggregation over that time period. So here's 4 seasons, each one 3 months long. And now you can start to see that those numbers indicate some amount of phenology. And now I might have enough information to be able to distinguish something like corn from soybean because they green up at different times. They have different amounts of greenness at different portions of the year. And so lots more information for the classifier to latch onto as you're trying to extract the information. You can go to far extremes with this. So there's lots of different ways to build a feature vector and include a lot of the temporal context. The sort of extreme edge of this is a process called CCDC, continuous classification. Gosh, my brain just shut down. I'll remember it in a minute. CCDC, detection and continuous change detection and classification. There we go, thank you. What this does is it takes the entire time series and it tries to fit harmonic fittings, tries to do a harmonic fit to the data. And as long as that fit is good enough, it continues. And as soon as that fit changes, like you can see here in somewhere around 2012, suddenly something occurred and it starts a new harmonic again. It starts a new fit and makes a new set of harmonics. In this particular example, it thinks that there are 5 breakpoints in this time series, and each one has a slightly different fit. Maybe it was trees going to cropland or cropland changing or something to that effect. But the cool thing about the CCDC coefficients, these harmonic coefficients, is that they're things you can classify on directly, and it works out. It's a little unintuitive that classifying on a cosine coefficient would work, but turns out it actually works quite well. So there exists in Earth Engine a time series of CCDC coefficients that you can use directly, and if it doesn't meet your needs, you can always just call the CCDC algorithm directly and reproduce something like this to capture and collapse the information in the time series down to a small number, a fixed number of coefficients that you can then use in your classification. Taking this even further, there are researchers that have successfully used Earth Engine to do full double sigmoid fitting for green up and green down signals. There's a paper that shows you how to do this. I haven't done this. I've read the paper, but I've never actually used their tools. But they're able to find, the middle of the green up and the middle of the green down and the peak of the growing season and all those sorts of things, and then use those as the classification feature vector, which then is super diagnostic for things like crop type in particular regions. Okay, onward. Oh, one more. You might have seen earlier today, or you might go to a session yet about dynamic world. This is a project that happened by a team here at Google where they took every single Sentinel-2 image and they applied a deep learning model to do a Landcover classification to that data set. And so here's an example of just one point in time. It's got 9 classes. I'll read through them. Water, trees, grass, flooded vegetation, crops, shrub and scrub, built, bare, and snow and ice. These classifications, these types, classes, may not conform to the definition that you want. You don't know, just by looking at this, what their definition of tree was. Is it just things above 5 meters or a certain height? But if you're going to build a classification on top of this, it doesn't quite matter what they did. In addition to just saying this pixel is full of trees, they actually have a probability. So this pixel is 30% probably trees and 12% probably wetlands and 1% probably snow and ice. And that particular combination of probabilities actually works out to be quite diagnostic for other classes. So you can classify using this as your feature vector, and it will essentially reformat the map to the definitions built into your classes. You've got a forest class that means deciduous, taller than 10 meters, whatever it happens to be. But if that's baked into your training data, then using that training data with this data set as a feature vector allows you to redefine the classes to meet your definition. So it's ongoing work. This data set exists. You can use it now. How well it works is sort of being uncovered right now, but it seems to work pretty well. So instead of building time series composites on your own, you might consider just using dynamic world as your feature vector and try to build your classification on top of it. And if it works, we are super excited to hear about it, so please let us know. And if it doesn't work, similarly, please let us know. All right, moving forward, that was all about temporality. I found this quote in a PhD dissertation that I was reading, and it seems to be, in my experience, quite true. Any amount of texture that you can include in your classification typically makes it better. And there's a couple different ways to do texture metrics or texture in Earth Engine, and I'm going to show you a couple of them right now. So, let's say you've got a 3-band RGB image, and you want some texture. The simplest possible thing you can do is just take all 9 pixels around every input pixel and extract them into the feature vector. And so this isn't exactly texture, it's just neighborhood. It makes for a very big feature vector. So if you, these 3 bands go from 3 classification, your feature vector being 3 elements long to your feature vector being 27 elements long. And if you make your window bigger, if you made it 5 by 5 or 9 by 9, you would include a lot of neighborhood information, but your feature vector might become unreasonably large. And so another way to do that, the function to do that, by the way, is called neighborhood to bands, should you want to use it. It just turns it into a bunch of bands, you sample the bands, and then you move on. A thing you might want to do instead is some kind of statistical reduction over those areas. So maybe you want the standard deviation of my 3 by 3 neighborhood. That would tell you how crunchy your data is. Or maybe you just want the mean, or the min, or the max. You can pick what statistics you want to compute, and reduced neighborhood will let you compute that for every pixel. And so in this case, if I was just taking the standard deviation, I would, instead of having 27 new elements in my feature vector, just boil that down to 3 again, which might be good. And then there's one whole separate function that will compute published texture metrics. It's called GLCM, gray level co-occurrence matrix. The way it works is for every pixel, it takes all of the neighboring pixels and computes a 2D histogram against all of those. And then there's some 14 metrics that are computed from that histogram. Covariance, contrast, entropy, correlation. The IDM is information dissimilarity metric. I don't know what that means, but it's a whole bunch of metrics that was published by 2 researchers in the 70s, and they're available where you can just say, I don't really care, just run some texture, and I will include that in my feature vector. It's pretty common. It's a little loosey-goosey, but it tends to work out. Okay, and one more piece to talk about is object-based image analysis. So this is a difficult thing to do in Earth Engine. We're not really built for it, but I built some tools in 2018 to help do this. The primary one is called SNCC. Superpixel non-iterative clustering, I think is what that's for. And that's based on another algorithm called SLIC, superpixel linear iterative clustering. So this is the non-iterative version, which fit into Earth Engine, whereas the iterative one did not. And then that will build you superpixels. So it'll find pixels that are similar to each other, group them together, and then you can treat that as an object and massively reduce the amount of classification you have to do, because you're just classifying for essentially 1 pixel of your object. But then you can do all kinds of reductions based on those objects. So you can get not just things like the mean colors of my object or the min or the max or those sorts of things, but you can actually start doing full, what are those called? Image moments, which tell you things like orientation of a patch, eccentricity, ellipsoidalness, those sorts of things. It was in and of itself an entire hour-long presentation. I've linked to it here where you can see the presentation and the video, which tell you sort of how it was the state of the art of object-based image analysis in 2018. 4 years later, there's a little bit more going on, but there's links there to those 2 pieces. That's my last slide. I'm going to hand it off to Emma, and she's going to talk about some work she's been doing on ensembles.
Thanks. So, how are you doing? Hope you're enjoying this nice session about classification. So, Noel talked about some tricks in order to improve the classifiers in order to get nice crop classification maps. So in this case, I'm going to suggest you some work that I did it before, where we are going to try to enhance our classifiers and make them stronger. Crop classification is a really complicated task. If you have a lot of temporal information, if you have a lot of, you can also extract features, as Noel tells you, about spectral, spatial, and it's possible to obtain strong classifiers. But there are some cases that we are not in that case. So, sorry. There are some cases that we are not in that case. So sometimes we have a very short number of training samples. Sometimes we try to classify two different type of classes that have the same type of phenology calendar. And some cases also we try to classify big areas that one class has different type of characteristics, spatial or spectral characteristics. So we can create weak classifiers at some point, but we don't want to finalize our work with that weak classifier. We wanted to get a really nice crop classification map, and in order to do, we can improve our classifications. How we can do that? We can create the weak one, 60% of accuracy, using a random forest model, for instance, or we can also create different type of weak classifiers using support vector machines with RBF kernel or linear kernel, polynomial kernel, or we can create much more number of weak classifiers, and then we can try to compose the final results of them in order to obtain a really strong classifier. So that was the work that I did it time ago. It's already published. You can look for the paper and download from the web. And in this case, in this work, we developed a classification chain of ensemble classifier. All the chain was developed in Google Earth Engine. So we started with some data, worldview 2 data, and then we focus to try to classify different type of 5 different base classifiers. So in that case, we select different combination rules, and the combination rules are based in a weight. So the weight can be obtained using the overall accuracy of the different base classifiers, or can be obtained using the kappa index, which is another statistical measure in order to evaluate our classification, or we can obtain also a value derived from one of these two statistical measures. Once we have our weights, we can combine our classification and we can get a strong classification. So how we can do that and how this is working? This is the important step. I prepared a simple example in order to show you how we can create an ensemble classifier. In this case, I have 3 different models, so I have 3 different classification maps. The 3 of them are weak classifiers, not higher, the accuracy, the kappa index is not higher than 0.65, and we are going to focus in the first one. So we have there one classifier that contains 2 classes, blue and red, and we are going to take the class number 1, and we are going to create a binary matrix using values equal to 1 in the pixels that we have the class 1, otherwise we are going to put it in 0. So now we need to know our weight. We need to know how much we are going to ponderate our models. So we are going to use an equation in order to obtain the weights based on the kappa index. In this case, as we have 0.58 kappa accuracy, our weight is 0.32. We only apply the equation. So we take that weight, and we can multiply our binary matrix from the class 1, and we can get a weight matrix from the class 1 for the first classifier. We can do the same for the class 2. We can construct our binary matrix and apply the weight that we obtain for the classifier, and then we have 2 weighted matrices, in this case, one for the class 1 and the other for the class 2. But remember that we have 3 different types of models in this case, in this simple example. So we are going to have the same 2 matrices for the model 1, and we are going to have the same for the other 2 models. At the end, we have 3 different matrices, weight matrices for the class 1 and 3 different for the class 2. We need to do something with them. So we are going to sum all of them, and we are going to get the weight matrix per class that we are going to apply in order to get the ensemble classifier. So using these 2 matrices, as we wanted to improve our classification, we are looking for the maximum value of the matrices. So for instance, we can take the pixel at the corner, and then we can choose, we can select which one is the higher value of the weights. So as the higher value comes from the class number 1, our ensemble is going to have class number 1 in that pixel. We can do the same for other pixel. In this case, the maximum weight comes from the class 2. So the results in the ensemble in that case is going to be the class number 2. As we can do the same for all the pixels that we have in our study area, at the end, we can generate a classification map from the ensemble, which is going to be a stronger classification than the weeks-based classifiers. So we can implement that in the Earth Engine code editor. I prepared a demo that I'm going to show you later, but in this part of the presentation, I'm going to highlight the important measures that we need to do in the Earth Engine code editor. So the demo that I prepared is going to split in 2 scripts. One of them is going to focus in the base classifiers. So as Noel explained before, is needed to training the different type of classifiers. In these examples, we have only 5 different classifiers, but you can increase much more until 100, 200 numbers of classifiers. So the important thing in this case is calculate the weight. Remember the equation that I showed you before? So you need to calculate in the code editor the weights of our base classifiers. So once we have that and we training our base classifier and we obtain the classification map of our base classifier, we add the weights as a property of our classification map per base classifier. We can do that for all our base classifiers, and then we can save in the assets all our classifiers in order to use the script number 2. So the script number 2 read the images that we have in the assets, and is going to apply the combination rule in the ensemble. In this case, we need to create, or we need to construct a function which is reading per class. Remember that we are going to have 1 weight image per class that we wanted to classify our classification map. But inside of that function, also we need to work in the different base classifiers. This is the complicated part. So in that case, we are going to have per classes the different results for each classifier that we have. And at the end, we are going to sum, which is the last line before the return. So we have an image collection that is going to provide 1 image per class that we have in our classification map. And then each image is going to contain 2 bands. One of it is going to be the value of our weights, and the other is going to be the number of the classes that correspond that weights. Then we can reduce using the reduce maximum function our image collection, and then we are going to get our final image, our result. In that case, our final image is going to have 2 bands. One of it is going to be the weights, and the second one is going to be the classes that are the final results of our ensemble. So before to show you the demo that I prepared, I'm going to announce 2 important things that I would like to tell you. So one of them is that if you are working with crop classification maps, this is going to be in the following months a new product, which is the European crop map of 2022. This map was done in collaboration of BOKU, my university, and the Joint Research Center from the European Commission. This is the update of the EU crop map of 2018. But in this case, we are not going to provide only the 27 European countries. Also, we are going to provide the new map from Ukraine. And the second announcement that I would like to tell you before show you the demo is that if you are interested to work or to know how to work with Google Earth Engine, the Austrian Agency of Science, the University of Valencia, and BOKU are preparing the Google Earth Engine European Summer School for the next April. 3 Google developer experts, Mathieu, Alvaro, and me, are going to teach in that course, and it's going to be from 2nd of April till 5 of April in Austria, Vienna. So you need to know that registration starts soon, next month, and how to see you some of them in Vienna next year. And now, yes, finally, I'm going to show you the demo that I prepared. And this demo was I have internet connection. Yeah, sorry. So this demo is focused on in agricultural area close to Vienna that I would like to thank Francesco Buolo, my colleague, because he provided me the fieldwork data that I use it in this example. This first script is the first script that I told you, which is the base classifiers. That in this case is we calculate we train in the classifiers, we calculate the overall accuracy, and we calculate the kappa index. Here you can see, we calculate the kappa index, and then we introduce that kappa index as a property inside of our classification map per base classifiers. The most important script is this one, is the second one, which reading the images that we save in the assets, we can calculate the result of the ensemble using the function that we created and I explained you before. And then we can provide the different overall accuracy and kappa statistics for the different base classifiers, and at the end also we can get the results of the ensemble classifier. Things that you can try in these scripts, one of it is to change the weight that we assign to the ensemble classifier. In this case, I choose the better results that we obtain for the manuscript that I showed you before. But if you go here, you can change and you can use only the overall accuracy, or you can use only the kappa index, or you can create the weights as the same way that I did it. The last thing that I would like to tell you is the scripts also provide the results by the console, and also you can visualize the different results of the base classifiers that we create and the final results of the ensemble. So thank you very much for your attention.
So we actually have time for Q&A. If you have any classifier or land cover classification questions, there are 2 microphones in the back, and we'd be happy to answer any questions you might have. Uh-oh, no questions.
No questions.
Hate it when that happens.
Siesta time.
Lunch was good, I guess.
Just to start to hit up. Each classifier has a lot of definitions and configurations. Some of them are different balance of samples. Sometimes you have to be very careful to use just the classifiers without this balance of the samples, because you have, sometimes it's better to take more time to improve your classification, like random forest, than to use others without too much care about the consistency of the classifier. Just to alert, to be careful, to just use a lot of classifiers without very good specification, and maybe sometimes, like, if you spend like more time adapting, balancing your samples using random forest, you could have something very nice, and with the multi-probability, you can analyze even the probability of the class of each pixel. So just to make a point here, it's a very good. We tried this kind of approach, and it's a very good solution, but be careful with the details of each classifier, because each one has different balance, and you have to work in the samples of each classifier.
I totally agree with that. In the demo that I prepared, I not optimize the classifiers, but in real, you should do that. You should optimize the individual base classifiers, try to get the maximum accuracy or maximum kappa, and then combine the ensembles. But sometimes, even if you do that, depends your application of in the classification, your accuracy is not going to be super high, and in that case, this is the ensemble when appears and then improve the results.
Yes. So, just regarding the ensemble of the old classifiers in just one output, how did you deal to merge all of them in one output? And maybe if it could be a good idea to use like a MLP, a multi-layer perceptron, to merge this ensemble thing.
How I did it is in the way that I explained during the talk, that you calculate the different weights for the different classes, and then you combine the results. For sure, as more sugar, better, more sweet. If you use neural networks, or if you use deep learning, also you can use them as a part of the base classifiers, and then combine the results of them in the final result. The thing is that, as far as I know, if you wanted to use neural network, you need to pass by Google Cloud, and this was an example of a JavaScript co-editor. So, and in that case, we don't have the possibility to use neural network. Yeah, of course.
Just to be complementary, but you have the multi-layer perceptron classifier in the code editor.
You can use it then.
You use that. So
I didn't use it, but you can use them, yes.
Okay, but I just trying to figure out if it's not a good idea to use the MLP, the multi-layer perceptron, as an ensemble algorithm, just to merge every algorithm into one output. So.
Yeah, it's possible. The type of model that you decide to use is decided by the user. And of course, if you have other options also, you can try to use them. Yeah.
Healy et al. Has a paper in 2018 that uses random forest as the merger. So you don't really care what the definition is. The random forest works it out at the end. So another option.
Yeah.
So thank you for coming, and enjoy your break.
Yeah.